Okay, welcome back, everybody. As usual, if you have any comments or questions, please post them to the chat or raise your hand, and Daniel will either answer them directly or alert me, and will stop the lecture and ask the question. I see that the number of people who are logging into the online class is dropping. The number of people who take the class is not changing, so this means that a lot of students decide to watch the video. I must say that this is not unusual. We see it also when we have in-person classes, that the attendance starts to drop during the semester. And I always say that even if you can look at the videos, and of course in this case we post everything including recitations, I highly recommend, if you can, to attend the lectures themselves. First of all, you know, if you watch it anyway, why not attend it when the class is given? You know, 11:40, at least on those for the East Coast, it's not too early. And the other thing, of course, is that it's much easier to ask questions or to follow some of the things that we are doing when we are doing it online, you know, the Piazza polls and everything. So I highly recommend that you try to stick to the lectures if you can, even if you can watch it offline. Okay, so today we continue to discuss support vector machines. And so support vector machines, we explained the name. So we said support vector machine are a classification method. They can be used for regression, but they were really generated and developed for classification. We are talking about supervised learning, you know, even in a larger context. And within supervised learning, we are talking about classification, so discrete outcomes, and specifically support vector machines, even though we'll discuss at the end how to extend them to multiple classes. The basic formulation of support vector machine is for two classes. So two class classifications. However, we wanted to use the idea of regression. So this WT, we wanted to still use it for classification. And we said that even though we wanted to use WTX, right, some parameter times the input, we didn't want to select and find linear separations, right? We didn't want to select the line that is closest to the point. For example, the line that minimizes this square, which is the solution that we would get from the regression problem, because we said that's not necessarily the best target function for classification. So then we asked, what is a good target function for classification? And we said one idea is max margin. Max margin means that the line doesn't care about all the points like linear regression line, but instead it only cares about the points that define the boundary between the two classes. And for this point, we want to be very far from both of them. So this is the idea of support vector machine, or max margin classifiers, which support vector machine is the most famous and most used representation. And that's what we derived. And we derived this idea by trying to represent the margin with the parameters. And we did some derivation and found out that if we minimize this optimization function, WTW, and subject to the constraints, we will indeed find the line, and assuming that the data is linearly separable, the line or the plane, right? Because X could be multidimensional. It doesn't have to be a univariate value. It could be a multivariate parameter input. We will find the plane that is maximizing the margin. Basically, that is the farthest from both of the closest points on both sides. So this is the linearly separable case. We derived it here, and we said that this works in some cases, but in most cases, the data is not linearly separable. So instead, or we extended this idea to include errors, but we want to minimize not the number of errors. We said that would be great, but it's very hard to derive. So instead, we want to minimize the magnitude of the error, which we defined as epsilon, and we had some weight to weight the difference between the margin, which is this part, and the error. And that's where we ended up. And, you know, we did some, or we went through some poll that in which I argued that C has an impact on the number of support vectors. So if C is very large, we're going to have relatively few support vectors, and if C is very small, we may have more support vectors. So C has an impact on the number of support vectors, but other than that, it can be applied. And so once you have that, you still have a margin here, although you make some mistakes. And you pay a price for these mistakes, but that's okay. So this is where we ended up. And we also said that both of these things can be solved using a quadratic programming solver. Okay, so that's it. Now, one thing to note, and it may seem trivial, but you will see in the next few slides that we can change that, is that the number of parameters in the linearly separable case is equivalent or is equal to the number of features in our data, right? So the number of parameters W is the number of features plus 1, because we have this B thing. But it basically on the order of the number of features. Here, the number of parameters is the number of features, and epsilon is also an unknown, so it's also the number of samples. Okay, so the number of parameters here is the number of features plus the number of samples, and here it's just the number of features. Okay, but in both cases, the number of features is part of the parameter set, right? I mean, in both cases, we have W. Okay, so this is definitely one way to define the max margin classifier, but it turns out there's another way to do it. So the same optimization problem can be defined in a slightly different manner, or very different manner. And the big advantage there is that we are moving from working in parameter space to working in sample space. And first, I'm going to show you the derivation of this new optimization, which basically tries to optimize the same problem, okay, but slightly different solution. And then we will discuss why this might be a useful direction, or where can this help us, okay? But first, let's ignore why we are doing this and just try to do this change in parameterization, basically from parameters in the feature space to parameters in the sample space. Okay, and this will lead to a different optimization problem. So let's start with the optimization problem we defined, right? It's mean of WTW, where for all samples in class 1, we want WTX to be greater than 1. And for all samples in class -1, we want WTX plus V2 minus 1. Now, we can write this as a joint. So these are two different inequalities, one for each class. We can also write it a bit more compactly as this. So we still have the same minimization function. And now, because y, right, y can be, we can basically multiply by yi on both sides, right? So if y is 1, then this becomes WTX plus, then we don't have to change the direction of the sign, right? Because if y is 1, if it's positive, we don't have to change. If y is -1, we have to change the direction of the sign. So this becomes greater than this, right? And this becomes 1, because -1 times -1, and this y. So this is the same. I didn't change anything. I just combined the two sets of inequalities into one representation, and it will be slightly easier to work with. Okay, but other than that, this is the same minimization problem, just slightly different. I'm using yi, which is an input, right? I didn't include it here, but it is an input, so I can include it into this inequality. Very good. Okay, so now we're going to define something called the dual representation of support vector machine. Basically the same optimization function, but slightly different parameterization. And for that, we are going to use something called Lagrange multipliers. Lagrange multipliers are ways, or are a way to solve a constraint optimization. So this is a constraint optimization problem. What is a constraint optimization problem? Constraint optimization means that we have an optimization, we're trying to optimize a function under some constraints. This is the function we are trying to optimize, and these are the constraints. So this is a constraint optimization problem. The problem with constraint optimization problem, or a problem, is that you cannot take the derivative, because the derivative will not apply to the constraint. So you have to do some iterative analysis, right? This is what we do in QP. But it would be nice if we can combine both of them into a single optimization and then take derivatives, because then this becomes a continuous problem rather than just an inequality and optimization. And it turns out that this can be done using something called Lagrange multipliers. I think in the problem set, in the recitations, you will go through some examples more, but generally speaking, Lagrange multipliers, the basic idea is that you take an optimization problem, in this case, we want to minimize x squared, let's say, and we have some constraints that x is greater than b, right? If there were no constraints, then obviously x would have to be 0. That's the minimum. But we have a constraint that x has to be greater than b. Okay, so this is a constraint optimization problem. And it turns out that you can combine the two using another parameter called alpha that has to be positive, but other than that, it can be anything. And this becomes a min-max optimization problem. And the constraint is now inserted into the optimization. So now we had the optimization and the constraint, and here we have only one optimization function. It has two parts. It has, for any x, it tries to find the maximum alpha for this function. Why would this work here? It would work here because if you select an x such that x is less than b, you're allowed to select any x, of course. But if you select an x such that x is less than b, for example, if you select 0, which we know would minimize the x part, then this part is negative, right? If x is less than b, then this part is negative. If this is negative, then infinite alpha would maximize this function here. But an infinite alpha would lead to very, very, would lead to a very bad outcome because this is negative, so this will be very high. So for x, it wouldn't be a good idea to select an x that is less than b, right? The way it works is that first we select an x, then we select an alpha. But x has to take into account the fact that alpha can be, different values. So for x to minimize this function, it would have to be an x where x minus b is greater than 0. Otherwise, the alpha can completely ruin the minimization by selecting an infinitely high alpha. Okay, so the idea is that when you insert the constraint or the inequality into the function, it leads to a joint optimization function that when you solve it, you get the solution for your original value, which is x in this case. Also, you get a solution for alpha. But that's not our goal. Our goal is to get x. So this is a way, again, the idea of Lagrange multiplier is not something we are going to present, or hopefully you have at least heard about it before this class. But I think the global idea is that this is a way to turn constraint optimization problems into optimization functions or continuous optimization functions that can be. In most cases, you can do the derivative. Okay. Now, in order to find the solution, you have to take the derivative with respect to x and with respect to alpha and solve such that it would work on both. So maximize with respect to alpha and minimize with respect to alpha, or you have to show that that's the case. And then you will have the combined solution for these two problems. And then you just find the x that minimizes this function. Okay, so this is the idea of constraint minimization, of dual representation using Lagrange multipliers. And now we want to apply that to our problem. Our problem, again, is this problem here, support vector machine, which is an optimization or constraint optimization problem because we have mean and an inequality. We have a lot of inequality constraints, so we need a lot of alphas, right? Alpha, for each inequality constraint, we need to introduce one alpha. In our case, we have several inequality constraints. In fact, we have the same number of inequality constraints as the number of samples. For each one, we introduce a new value alpha. In Lagrange multiplier, sometimes alpha is denoted by lambda. I'm going to use alpha here because we use lambda in other cases. But if you are familiar with Lagrange multiplier, usually sometimes they are called lambda as well. Anyway, so this is the new. This is the Lagrange multipliers applied to this problem. So we take the optimization, we put it here, mean on W and B, which is the parameters, right? Like X, W, T, W over 2, which is what we wanted to obtain. And then we take the constraint and we insert it into the optimization. So minus alpha I times WTX plus B, right? The constraint has to be 0. So we move minus, so this becomes -1 greater or equal to 0, and we multiply this by alpha. Okay, so the constraint has to be greater or equal to 0 for Lagrange multiplier to work. So we put the -1 here, but other than that, this is exactly the same. And we sum over them because we do it for the first one plus the second one plus the third one and so forth. Okay, so this so far we didn't do anything, but we reparameterized the problem. So now we have W's, which remember W's, this is for, I should say, this is for the linear, we are working on the linearly separable case. Hopefully everybody sees, because I'm not using C here, right? So this is the linear separable case. So in the linearly separable case, we started with parameterization in the feature space, and now we still have parameters in the feature space, which are W's, but we also have alpha i's, which are in the sample space. So for each sample, we have an alpha I. Okay, so this is the Lagrange multipliers. The next thing we want to, or the next thing we do in order to find the value of, in this case, W or the general the parameters, is we take now the derivative with respect to that parameter, but we also need to take the derivative with respect to the alphas, to the Lagrange multipliers themselves. And only by combining these two, we will find solutions that agree both with the constraint and with the optimization. So the next step is taking derivatives with respect to the different parameters we have. So we have parameters for W. In fact, for each Wi is a parameter, and we have parameters for alpha. So when we take the derivative, we get these three equations. First, when we take the derivative with respect to W, I can. So when we take the derivative with respect to W, W is a vector, right? So we can, WT, W, the derivative with respect to W, it's like taking the derivative of a square value. So it's like, in this case, so this is what we are trying to take the derivative for. So it's 2WT over W, over 2. Right, so this is like taking a derivative of something square. So we get, this is WT, W. Okay, so the derivative of WT, W over 2 is W. Okay, that's the other place where W appears is in the constraint, right? So we have for each I, we have alpha I, W, TX. And also, if you, I think we also have it times, let's see. Why? Right, yi. Okay, so if we take the derivative with respect to W, and this is minus, and a sum. So if we take the derivative with respect to W, we get W equal, and equate to 0, we get W equals sum over I, alpha I, xi, yi. Right, let's see. Right, so this is what we get. Okay, so this is what we get. That the W basically equals this. When we take the derivative with respect to W, this is. Yeah. So when we take the derivative with respect to W, we basically get that W equals, right? The W equals sum over I, alpha I, xi, yi. Alpha I and x and yi are univariate values. They are just one value. Xi is the vector, the same dimension as W, so that's fine in this case. When we take the derivative with respect to alpha, we basically get back the constraint, right? Which is basically WT minus 1 equals 0. So we can move it to the other side, multiply by yi. And basically yi times yi is always 1. And 1 times yi is always yi. So that's what we get. The only thing I would say here is that when you take the derivative with respect to alpha, you have to be slightly careful. Why is that? Why do we need to be careful when we take the derivative with respect to alpha I? Anybody can tell me? So again, we took the derivative with respect to W, which is the X in the original Lagrange, and we showed that this leads to W equals sum over I, yi, xi, alpha I. That's good. The next thing is we take the derivative with respect to alpha I, and we can get basically that, in this case, that we get that WT x plus B equals yi. That's good, but you have to be a bit careful when you take the derivative with respect to alpha I. Why is that? Anybody can tell me? Where do we need to be careful? Exactly. Good. So the answer I was looking for is the answer that some of you have written in the chat. Alpha I has to be greater or equal to 0. That means that there is a discontinuity in alpha I when we get to 0. Because it cannot go lower than that. This means that anything above 0 is continuous because it can go, I mean, we are talking about continuous values. So it can, but we cannot take the derivative if alpha is not 0. So the only alphas, so if alpha is 0, it's 0. If not, we can take the derivative. And in that case, if you take the derivative with respect to alpha and you assume that it's not 0, then you get that bi equals yi minus wtxi for alpha i's that are not 0. For alpha i's that are 0, we are not taking the derivative, okay? Because they're 0. But for alpha i's that is not 0, it's continuous. It can go all the way down to 0. There's lots of space between any value and 0, so we can take the derivative, and this is what we get. I mean, this is pretty easy to take the derivative with respect to alpha. Okay, so this is what we get from inserting the Lagrange multipliers and taking the derivative. Now let's see for before. So this is not good enough, but let's see in a second. Let's see first what is the interpretation of what we got here. Oh, sorry. If we take the derivative with respect to B, we get oh yeah. So if you take the derivative with respect to B, you have basically alpha I B Y I alpha sum over I alpha I B. If you just take B out, then it's sum over I B Y I. So you get sum over I alpha I Y I equals 0. If you take the derivative with respect to B. Again, that's pretty simple to do. Okay, so these are the three derivatives that we took. We took derivative with respect to the parameters, which are W and B. This is what we got for W, and this is what we got for B. And we took the derivative with respect to alpha, and this is what we got for all alpha is greater than 0. What does it mean? Well, remember, W is our parameter, right? Now, if we want to get W, we have to sum over alpha I, xi, yi, right? This is the values that we get for W. For some of these xi and yi, alpha I is 0. We don't know which, but for some of them it's 0. For the others, it's non-zero. It's clear from here that the ones that impact W are only the ones that alpha is not 0. If a sample is 0, then we are not using the xi and the yi of that sample. We are not using it for W at all. We're only using for W those xi and yi's where the alpha i's are not 0. On the other hand, we said when we talked about support vectors, that support vectors are points that impact the value of the margin, or in this case, W. So this is a simple way of finding the support vectors. If you have an alpha I that is 0, you're not a support vector. The only ones that are support vectors are the ones that have alpha i's that are not 0. Again, we didn't say how to find alpha I, but if we know how to find alpha i's, we can easily find what are the support vectors. Before we said the support vectors are the ones where, remember we said in the previous lecture where WTX plus B equals exactly 1. So we need to, that's or minus 1. In this case, it's even easier. When we have alpha i's, we just look at them. If you're 0, you're not a support vector. If you're anything other than 0, you have to be, alpha I has to be positive, then you're a support vector. Again, we didn't say how to find it, but just an observation. If we know alpha i's, that's something we can see. Okay, so basically, all of the support vectors have a alpha I that is greater than 0. All of these have alpha i's that are 0 because they're not support vectors. They're not impacting them. Okay, but this is not enough for us. We still want to get a slightly less complicated function. So this is, again, this is the optimization function we had. Remember, this is the min max with the Lagrange multiplier, and then we took the derivative, we got to some constraints. And now we want to use these constraints to change the optimization function. Or in other words, we would use these constraints to remove some of the parameters we have here by replacing them with the parameters we have from the derivation that we did. Because, for example, W equals this, we can, every time we see W, we can just put this in, because that has to be W. Again, we don't know what alpha I is, but when we find it, this will be. Okay, so how do we do this? So for that, again, let's use what we wrote and then try to reconstruct the optimization function using the values we derived. So the first thing we have is WTW. And we said that W equals sum over I, alpha I, xi, yi. In that case, WTW basically is this times itself, right? So this times the same sum. And if you open this up, you will see that this comes down to sum over I and j, alpha I, alpha j, which could be the same. I mean, all pairs, xi, xj, yi, yj. Well, this here is something called the dot product. So this is basically point-wise multiplication of every entry in xi by every entry in xj. All the others are just values. They're not vectors. But this is WTW. So we can write this as alpha I, alpha j, xi, xj, yi, yj. Again, if you just write it as two sums and multiply them, that's what you will get. I and j can be the same or they can be different. I mean, so we go over all pairs of samples, the same one and the same one. So this is one part of the equation. We also have this sum over I, alpha I, WTX plus B, YI minus 1. Okay, so again, we replace, when we replace W, so this basically equals sum over I, alpha I, WTX, YI, right? Plus sum over I, alpha I, B, YI, and basically minus, this is all in minus, right? This is all in big minus. And so this is, everything here is in the minus. And then we have also, so everything, this is minus this, minus this. And plus alpha I, sum over I, alpha I, right? Because this multiplies by minus 1 and the minus. Okay, so we have plus, we have sum over I, alpha I, that's part of the thing. Now, what about this? Alpha I, xi, yi times WT is exactly the same, or we can take WT out, right? Because it's not a function of I. And then we basically get the same thing we had before, right? Sum over I, alpha I, xi times sum over I, alpha I, WT, xi. So it's exactly what we derived before, right, in the previous one. So this is exactly this thing here. This was over 2, so this is also over 2. But other than that, it's the same. Sum over I, alpha I, we don't have a lot to say. Now, what is alpha I, B, yi? Or we can write, again, B is not a function of I, so we can write it as minus B, sum over I, alpha I, yi. What is this? What's the value of this function? Anybody can write to the chat. That term disappears. Why does it disappear? Because it's 0, exactly, right. Very good. So we already said that sum over I, yi, after we took the derivative, is this sum here is 0. So minus B times 0 is 0. So this goes. And after all of this derivation thing, we get to the following set of equations. So after we did the derivation, basically, we get sum over I alpha I that we got from the last part here, alpha I times the -1. And then we had this thing here as alpha I, alpha j, yi, yj, xi, t, xj, basically a dot product between the two. As here we got it as over 2 in the plus side, and here we get it as without over 2 in the minus. So this minus this is 1/2 of this thing here. And we still require the alpha I, yi equals 0. So we still use it here. And alpha I, of course, has to be greater than 0. We don't need to use this because we don't have W anymore in our equation, if you see it. And we don't have W and B here, so we don't need this. But we still have alpha I and Y, so we use it here. Okay, so this is the equation we got from basically substituting everything we derived into the optimization function. And this is the new optimization function that we got. This is called the dual formulation of support vector machines. And there's a few interesting things to notice when we look at this. First, W disappeared from our parameter set. All the parameters we have here, or the only parameter we have here, is alpha I. Alpha I, we said the cardinality of alpha I, or the number of parameters we have for alpha I, is the number of samples. It's not the number of parameters. Here we had the number of parameters. Here we move to a different, it's still parameters. We don't know the value of alpha I's, but the number of alpha I's is the same, or the number of alpha I's we need to find is the same of the number of samples, and it's completely independent of the, oh, not completely, I don't want to say completely independent, but it's not the number of features. This is good news. It's good news because if we now take data to a very high dimension, we already said, like if we have univariate data, we can represent it as a polynomial of degree 10 or 20 or 30, the number of parameters doesn't change, right? Everybody sees that? Let's say we take values and we want to predict an outcome. Let's say height, and we want to predict whether you are male or female, right? We said that we can basically turn the height into a polynomial, but that would require more parameters. More parameters can lead to overfitting. In this case, the number of parameters doesn't change because we're working in the sample space. We are not working in it. So that might be good. But I will show you in a second where this is really crucial. In some cases, this is really something that is very good. So this is definitely one thing we see here. The other thing is that we see that all the analysis we do is in terms of dot product between two inputs, right? So yi, yj, yi, yj are just values, so that's not a big problem. But the way we use the inputs is as a dot product. We don't have xi anywhere else. The only way we use xi is as a dot product with another sample xj, which could be the same. It could be also xi, but we basically sum over all the place. Okay, these are just observations. We will see in a second.
Someone has a question. Someone said, when doing the min-max here, does the order of the min-max matter?
So the order of the min-max in representing the, not representing, in writing the analysis matters. And the fact that we are minimizing with respect to W and maximizing with respect to alpha is important, okay? Now, what I haven't shown you and should be done and people have done is to take the second derivative and show that indeed whatever we did the derivative for alpha would lead to a maximization, and whatever we did the derivative for X would lead to minimization. We haven't done that, but that's, yeah, that is important. So it's not so much, right? So this has to be shown that you get this too. But the order does matter, yes. Yeah, so we are not maximizing for W, we are minimum. I mean, we take the derivative, it could also be minimum. It doesn't necessarily have to be maximum. But you have to show that this is indeed minimum or maximum. Okay, so this is for the optimization function and the dual representation. And this is the final thing we got, right? This is all in alpha space, but just some function that we have, max over I alpha I minus half something. And in this, we have dot product. So the only way we are using the inputs, or the only time we use them, is as a dot product with another input. We don't multiply them by another vector, for example, a parameter vector, right? We don't have a parameter vector. And the alpha i's are kept separate. We don't, right? We don't officially multiply. We only multiply alpha I by alpha j. We don't multiply alpha I, alpha. So we don't take the vector of alpha, or we don't explicitly use the vector of alpha. I mean, there's a way to do that as well, but the important thing is the dot product. And of course, this can be computed directly from the inputs. We don't, this is not an unknown. We can compute these values easily from the inputs. To evaluate a new, right? So this is the optimization function. Assuming that we solved it, let's say we solved this, we found the parameters for alpha I. How do we evaluate a new function? So there's two ways to do it. One is to derive W and B. We said that when we have alpha, we can derive W easily, right? W equals alpha I, xi, y. So if we know alpha, we can get W. And if we know W, we can get B. Okay, for the alphas and all. So that's easy. So that's one way. But another way is not to learn W and B, but to use the alphas directly, because we know that W is equal to alpha I, yi, xi, sum over them, right? So we can sum all of this and multiply this by xk. Xk can go outside the sum. It doesn't matter because it's not necessarily, right? But if we want to do the dot product, we can also do it inside the sum. It's going to be the same value. So this is another way to do it directly. We still need to compute B. But this is another way to do it directly without actually computing W explicitly, because W is also already computed as a function. Okay. Of course, in order to get B, in order to find B, we need at least one alpha I that is greater than 0. What happens if all the alpha i's are 0? How can we get B? Anybody can tell me? So again, right, B, we said we want to find. W, we know is just sum of this, but W can be 0. But let's say W is, I mean, if everything is 0, then W is 0. That's not a good way to solve, but it's a valid. But for B, we really need to have at least one alpha I not 0, otherwise there's no B. How do we know that we have at least one alpha I that is not 0? Anybody can tell me? Again, the question is clear. In order to get B, we need at least one of the alpha i's. If all the alpha i's are 0, we don't have a B. But we want to get a B because otherwise we don't know how to solve, or even if we have the alpha i's, we don't know how to assign the value. So how do we, what guarantees that at least one alpha I is non-zero? Anybody? So remember, we said, yeah, exactly. So that's the answer. Remember, we said that if you're a support vector, your alpha is non-zero. By definition, all support vectors are non-zero. We must have support vectors, otherwise there's no margin, there's no solution. And we assume this is linearly separable, so there is a solution and there is a, by assumption. Again, if it's not, we'll get to that. But for now, so there must be at least two, honestly, right? Because for the margin, we need at least one on each class. Alpha i's are for both classes. We need at least two, usually more than that are support vectors. So both of these will have alpha i's that are non-zero, and we can get B from either of them. It will be the same B, basically defining the function. Okay, so this is just, again, this is just a sanity check that we will always get B. So this so far has just been another way to represent support vector machines. But you know, I didn't say, or we didn't discuss why this would be useful. We did say that this is a different parameterization because it's moving to the a sample space in terms of parameterization. But other than that, why is this useful compared to the original or the former, right? The original representation of support vector machine. Why is the dual so interesting or so useful? So here's an example where the dual is actually pretty useful. So let's look at this data set. Okay, so this is 1D. We have two samples in class 1, two samples, the red ones, two samples in class -1. And clearly we can separate them, right? We can put a line or a line here. separate them, or a point here to separate them. That's pretty easy. But if we have this and we are working in 1D space, right? So we're working even in 2D, it doesn't matter. There is no line that will separate these 2 points, right? I mean, obviously it's clear that because they all share the same value for the y-axis, there's no line. However, if we transform this, so these are all points, let's say these are all points in 1D, right? So we are not changing. Y is the fixed. But if we move these points to 2D, so basically if I write x and x squared, instead of representing this point as one value, I do a transformation, which is just a function of the input. It's not a function of anything else. Then I can represent this as this. And now we can actually find a line that separates them. So now they become linearly separable. These are not linearly separable. Sorry. These are not linearly separable in 1D. 1D is just one value. There's no value that will separate them. But in 2D, and again, this 2D means that we change the representation of the input, they become linearly separable. What's the problem we said with that? The problem is that we need to add more parameters because now we have more values. We have more values for each of the inputs, more parameters. However, in support vector machine dual representation, we don't need to add more parameters. The parameter space is only a function of the samples. The number of parameters we need to estimate, the alpha i's, remains the same in this case and in the. So that's a very big advantage for support vector machine and dual representation compared to the original representation. And this is another example, right? In 2D space, right? There's no linear line that separates the red and the blue points. No linear line. There is a circle, but no linear line. However, if you transform them into 3-dimensional space, so you take x1, x2, and x1, x2, okay, and you know, you work in x1 squared, it doesn't matter, but it's just this 3-dimensional space. Now there is suddenly a linear line that separates them, okay? But again, the downside is that we increased the size of the feature space. And again, this is pretty small increases. We went to 1 to 2 or from 2 to 3, but you can think of much, much larger increases, right? So going from, let's say, 10 values to 10 square, because we go from, you know, all the individual, let's say we take, I don't know, some measurement with 10 values, some table that has 10 features, and we take all combinations of these features, x1, x2, x1, x3, and so forth as inputs, right? Not as x, now x1, x2 is not the sample, it's a feature in a sample, okay? So this will go from 10 to 100, or maybe cube. We'll take all triplets, 1,000, 10,000, and so forth. At some stage, we will just get to a very, very large dimensional feature space, which will definitely be overfitting. However, in support vector machine, we cannot overfit because the number of parameters is fixed. It's a bit tricky. It's not completely fixed, but it's pretty close to fixed. So as a statement, if the data is mapped to a very, very high dimensional space, then everything becomes linearly separable. At some stage, if you go high enough in the high dimensional space, unless the points are exactly the same, then you can start separating them linearly. The challenge is, of course, mapping it to very high dimensional space requires a lot of time because we need to store a lot of values, right? If we go from 10 features to 100 features to 1 million features, we need to, even if we don't need new parameters, we still need to compute these features because we need the xi and x, we need a sample. So that's one problem. The other problem that we don't have in support vector machine is the idea of parameters because we don't have more parameters when we go to high dimensional space. Okay, so this is something we discussed already in the context of linear regression, in the context of logistic regression, but we said maybe not so fast with the transformation because they introduce many more parameters. But in this case, they don't introduce more parameters. We still have another problem, right? So we don't have more parameters because support vectors, the number of parameters in the dual space is fixed. But it's still a lot of computational work, right? If I go from 10 features to 1 million features, I need to compute all these 1 million features, right? If I go from combinations of, you know, value, I get 10 values and I want to compute all combinations of, I don't know, x squared, x cubed, maybe, I mean, I go to 1 million features, then maybe I don't need more parameters, but I still need a lot of time to compute them and to represent them. I need a lot of storage to represent them. So the first answer for many more parameters we already discussed. The second is an interesting trick called the kernel trick. Here we use kernel in a very different way than we used it in the local regression sense. I mean, that's the word people use for support vector machine. And the idea is that you can do some transformation, not all transformation, obviously, but some transformation you can do without explicitly computing them. For example, you can move from 10-dimension space to 1,000,000-dimension space without computing the 1,000,000 dimensions, without storing them, but you will still work in the 1,000,000-dimension space. Again, that's not true for any transformation, but some transformation you can do. And if you can do that, then you solve two problems at the same time. One is you work in very high dimensional space, so you can get linear separation, but you don't need to pay the price in terms of overfitting because you don't have more parameters. And two, you don't need to spend a lot of time and computation on finding these million values because you can represent them pretty simply. So let's do an example and show how this works, and then we can. So these, or the first example we'll talk about is something called quadratic kernels. Quadratic kernels are kernels that use a value, a set of inputs, let's say x1 to xm, let's say, I don't know, pixels in a picture. So we have, let's say, I don't know, 4x4 or 8x8 or 32x32 images. Each one has one value for each pixel, and we want to represent it as the value plus the product of all the different pixels. So this becomes now square in the size of the input feature. So let's say one sample has m input values, and we want to represent this in a high dimensional space by m square values. So let's start with this representation. So we're going to have, rather than m values, we're going to have almost m square values by taking x1 and multiplying it by square root of 2, but still using the linear version of it. And then we take all the quadratic version of the single values, and then all the pairwise features. So this will take us to, we have more or less m linear terms and quadratic terms, but really the large number of terms is m square pairs of features. Okay, this is a possible representation. I mean, I'm not saying why this is useful, but this is definitely going to much higher dimensions. So we started with, let's say, 900, and now we have 900 square dimensions in our input space. This is good because now we are going to 900 square dimension. It's going to be much easier to do a classification of cats and dogs, for example, because we said already, if we go to a high enough dimension space, things become linear separable. We can use SVM to solve it. But the problem is that now, rather than working with 900 value inputs, we have to work in 900 square inputs, which is huge and also very time consuming. It turns out that in support vector machines, we don't need to do that. And the reason why we don't need to do that is because, as I showed you, all the computations we are doing are related to dot products. We don't multiply the parameters by the samples themselves. We multiply parameters by dot product of samples. So if there is a simple way to represent dot products, we don't care about the inputs themselves. The only thing we care about is how to represent simply dot products. And how do we do it here? So let's take a dot product of two samples that we transformed in the way we transformed it. So let's say x and z, right? Phi x times phi z. X, we transformed it by taking all the linear terms. Okay, so x, this should be xm. This should be xm, and this is xy, xm, and xy, and so forth, and similarly for z, okay? Okay, I can change it on the fly. Anyway, so this should be, right, rather than one, this should be x2 or xm, doesn't matter. I mean, these are the m linear terms, these are the quadratic, and these are the pairwise terms. Okay, so this is a dot product we need to compute. What is the computation here? Basically, it's a sum of all the linear terms times themselves, the sum of all the quadratic terms times themselves, and then pairs of xy, xz, zi, zj, right? This is just the summation that we get here. Okay, so this is, we didn't do anything, we just did the transformation. And if we have 900 square, we need to do it 900 square times because we have 900 square here, 900 square here, and the summation takes 900 square. So this is a lot of computation, but also a lot of things to see. However, right, so more or less m square by using the summation. However, it turns out that this can also be solved in a much different way. Let's look at, rather than doing the transformation and then doing the dot product. Let's do the dot product first and then square it. Okay? So again, I'm saying that we do a dot product plus 1. Again, y plus 1 and so forth. You will see in a second. But let's say that we do this as x times z plus 1. And that's easy because we can just put the values of xz. Right here, we also have plus 1 here. So if we do this, and we take the square, which is basically what we did here, right? 1 times this plus the dot product of these two, if we keep 1 out. Right, if we do this, then what we get is, right, this is all the linear, quadratic, and pairwise terms, and 1 is the value we added at the beginning of the input. If we do this, then basically this is just taking quadratic equation, so this is x dot z square plus 2xz plus 1. X dot z square, you can just open it up, but basically this is sum over I xi zi square. Again, we'll open this in a second. This becomes just sum over I 2i x zi, right? This is just sum over the dot product, which is basically, this is the dot product. This is just another way to represent the dot product. So this is all the linear term, and plus 1 comes from here. So this is the same as the linear terms we have here, right? This is this. This is the same as 1. And what about this? This is sum over all the xi zi times xi zi, so we get all the pairs of xi, all the pairs of zi, and the quadratic terms as well. So this is just splitting it up into things where xi, xj are the same, and those are not the same. But basically, this is exactly the same value. So if we do this, which requires only 900 operations, right? Because if we start with 900 value vector, computing the dot product is 900 operations. If we only do 900 operations, and square is 1 operation, so we only need 900 operations, and we don't need to represent the transformed value. But we still get operations in the transformed space. All the dot products we compute are in the transformed space. So even though we work in the original space, we don't need to do any computation to explicitly represent things in the transformed space, and we don't need to store the values in the transformed space. The actual outcome, if instead of computing dot product, we compute dot product square, is like we worked in the transformed space. So this buys us by using the fact that all the computation we are doing are only dot product. If that wasn't the case, it wouldn't work. But because all the computations, including not just finding the values, representing the optimization, but also solving the applying the classification itself is also in the dot product space, we never need to compute the actual representation. We just need to be able to compute what would be the result if we worked in the high dimensional representation. So this is a way, of course, here I did it square, but you can take it to the power of 3, power of 4, any polynomial, which is a huge number, right? Like 900 to the power of 10, 12, whatever. You can still do it in 900 space, but work as if you're working in the highly polynomial space. That's an advantage of support vector that is not true for others because they don't have this idea of dot products all the time. Okay, so again, this is only true because both the optimization function we need to solve only requires the dot product computation, and after we solve it, we don't need to have the representations or find W's, right? If we had to find W's, we would still be in a problem because it's nice that we can find the optimization in Xi, but now when we need to find W, we are going back to the feature space, which is very large, but we don't, because even for evaluation, we don't really need to find W. We can just do this. Okay, so this is nice, and in terms of the number of operations, rather than working in very high dimensional space, we only need to compute m times r, where r are the support vectors. We don't even need to take it. So this is much faster than before, and also much more space and time efficient because we don't really need to go to the high dimensional space. Now, kernels, again, you should show not all kernels can, or not all transformations would work. Because the transformations that work are transformations that can be computed efficiently by dot products. If they cannot be computed efficiently by dot products, or there is a simple way to compute them by dot product, they wouldn't work. right? If you now take some sinusoid of this and or log of that, it's not necessarily going to work because you can't apply the dot product. But people have worked for a long time on coming up with different transformations that do work. For example, any polynomial you can represent this way. You can do something called radial basis function, which is basically like a Gaussian that also works, tan H and so forth. And a lot of these things you will see again when we talk about when you talk about neural networks, but these actually started their life in support vector machines. So there are a lot, I mean, so the kernel idea, again, something that can be easily represented in high dimensional space, but can be something that can be computed easily by dot product, but actually represent a very different thing in high dimensional space is a very powerful method and works only in SVM because of this dot product thing. And in this sense, once you have that, you can actually now basically work as if you're working in very high dimensional space, move things to high dimensional space. Even if they're not linear separable in the original space, they are very likely to be linear separable in a high dimensional space. You solve the support vector machine problem, and then you have a solution that not only classifies correctly the two samples, but also has a pretty good margin, or at least attempts to have a pretty good margin. Okay, and then you can apply. So this is the idea of kernels and of dot product and of the dual formulation. And that's why we do the dual formulation. First of all, we are moving into another space, which is not affected by the size of the transformation, which is a big problem for us. And the second thing is that once we do the dual formulation, we move into dot products of all the functions of the individual dot products, and that opens the door to a lot of interesting applications. Okay, so I have a few Piazza questions, but before that, I wanted to ask you a question, and then we'll do Piazza poll. But this is like more about a bit more theoretical question. Oops, about that. So I said that when we move to high dimensional space, basically we don't pay a price because unlike in the primal, in the original representation where we get many more features, when we move to high dimensional, when we move to the dual problem, it doesn't matter how many features we have, the number of parameters is still fixed, and it's the number of support, and it's the number of samples, right? Alpha i's are always a function of the number of samples. It doesn't matter. However, that's not completely true. What happens when we move from relatively low dimensional representation to very high dimensional representation in terms of parameters? In the dual space, do we see any impact on parameters there, or we don't see any impact because we're all working in the sample space? Anybody can think of an impact we will have? Of course, if we worked in the primal space, we would have a huge impact. We would have many more parameters, one for each feature. Right. So the answer, as was mentioned in the chat, is that it's true that the number of alpha i's does not change, because the number of alpha i's is the number of samples that doesn't change if we move to very high dimensional space, because each sample now is represented by very large dimensional space. But it's not true that the number of support vector doesn't change. When we move to very high dimensional space, we have more and more support vectors because the dimension becomes larger and larger. We need more support for each of the transformations. And that means that even though alpha i's, the total number of alpha i's doesn't change, the number of alpha i's that are non-zero, or equivalently, the number of support vector does change. So the effective number of parameters does change. However, there is a limit. It cannot be more than the samples. So there is a limit to the number of features, but obviously the number of non-zero alpha i's is changing when we go to higher spaces. Okay, so this is something to keep in mind. Okay, so now let's turn to the Piazza poll. I have two questions for you. Okay, so let's discuss the questions that I asked you. The first question, which which you probably should have asked yourself is, okay, so we defined the dual formulation, but how do we solve it, right? We didn't say, how do we solve it? We said that we can easily, once we have any transformation, we can easily write it, but we didn't say how we solve it. So the answer is that, I mean, like with the original formulation, there are many ways of doing it. You can just take derivatives, but in fact, this is still a QP problem. So we still have, of course, constraints. So this is not a linear problem. We still have constraints. For example, alpha I has to be greater than 0. So those, it's definitely not an unconstrained problem. It's still a constraint problem. But not only is it a constraint problem, it's still a QP problem, because we have basically alpha I times alpha j, right? Or alpha I times alpha I in the optimization. We also have the linear term, which is sum of the alpha I. So this is still a linear, this is still a QP problem. You need to actually, once you have the samples, you can write the matrix. Without the samples, of course, we can't. But once we have the samples, we can write the quadratic matrix. The vector for the linear is just vector of 1, right? And then we have all the constraints that we derived, which are basically alpha I greater than 0 and maybe other constraints. Yeah, sum over I alpha I equals 0. That's another constraint, and sum over I alpha I yi equals to 0. That's a linear equality constraint, and we have the inequality constraint. Okay, so this is the answer to the first problem. So basically, again, so right, even though we mainly discuss QP in the context of the primal as a support vector machine, it also works for the dual. There are other ways. I mean, you can do other ways of, I mean, lots of different ways to solve it, but QP is probably the best idea. The second question I asked is about the number of parameters for a linearly separable case, right? So in the non-linearly separable case, it's different, but for the linearly separable case, that's why I asked. So we have n samples, and we have k-1 features, and we want to know. And we know that the resultant model had n-n1 support vectors. However, of course, we don't know which ones they are, right? So in order to find which ones they are, we need to define all the parameters for the QP, and then the QP will give us the answers. In the alpha I case, it will give us n1 that are not 0, and the rest are 0. In the primal case, it will just derive some W and B, and we can get that. But anyway, the question is, how many parameters should we define for the solver for this? And the answer is, basically we said, right, in the linearly separable case, the primal SVM works in the feature space. So it will need k parameters. So k-1 features plus b, which is another feature, so k parameters. And the dual space works in the feature space, sorry, in the sample space, only in the sample space. It doesn't know what are the support vectors, so it cannot use the fact that we know that n1 is the number of support vectors, because we don't know which one they are. So for the dual formulation, we would need n parameters. So for the solver, we would have alpha I parameters for each sample for the dual case, and k parameters for the features, right? k-1 for the inputs and b, which is okay. So this is the answer. So the first, so the first one is the right answer in this case. Okay, good. So this is okay. So we talked about other kernels. Two things we haven't discussed yet. One is what happens in the non-linearly separable case. So first of all, we said that using the dual formulation and the kernel trick, most problems can be solved in a linearly separable case by going to another dimension and then using linearly separable solutions. That's what we do most of the time. So we can go to high enough dimension, and eventually we will be able to solve it with no errors. However, there are cases where this cannot be done, or maybe cases where we don't want to go to very high dimensions. And in that case, we can still use the same formulation that we did for the non-linearly separable case in the primal, and then take the derivatives now with respect to the parameters that are defined there, which are also the alpha, which are also the epsilons. Okay, so now we have more parameters. Before we only had W and B, but now we also have the epsilons, so we need to take the derivatives for those as well. When you do that, and we won't go through that exercise, but you know, this is something that can be done. It's the same idea. So you define again a new Lagrange multiplier, but now rather than using the a multiplier for the equality, you use it for the inequality that is defined by rather than using the greater or equal to 1, we use greater or equal to 1 or less than minus 1. We do it for 1 minus epsilon, which is what we define for the nonlinear reciprocal case. And when you do that, you get very, very similar optimization functions. So the target function stays the same. The constraints on alpha iy stays the same. And this is the new constraint that we get. So alpha i's now are basically constrained to be greater than 0. They, of course, have to be greater than 0 by the definition of the Lagrange multipliers. But C now comes into play, and basically all the alpha i's have to be less than C. This is still a constraint optimization, so still a QP solver. So I mean, I'm representing this as 1, but this is really 2 different constraints. So alpha I has to be greater than 0, and alpha I has to be less than C for each. But again, so this is a new representation of the constraints. The meaning of C, the fact that when you increase C, you get less support vectors, as we discussed before, that stays the same. That doesn't change the way we define support vectors or anything else, okay? And again, once we move to the dual formulation, we can actually, in most cases, not use the non-linearly constraints, because if we go to a high enough dimension, things are linearly separable. But again, this can definitely be done in the dual formulation as well. So this is one point that we haven't finished. Yeah, so right, people have worked for a long time on trying to understand why SVM work, right? So we already said that the motivation for a max margin classifier makes sense, and you know, it's nice. But you know, can you theoretically show that this is the best way to classify? The answer is no. There are some theoretical results, but you know, there's no proof that this will work for all cases. But still, as I said, in practice, support vector machine as a standalone classifier, so not ensemble are different, but as a standalone classifier and without neural networks, which are really, you know, you can treat neural networks as standalone, but honestly, they do a lot of things with a lot of features. So they are also some sort of ensemble. But support vector machine works very well. And the reason why it works well is that basically the support vectors are putting some type of regularization on the function, or sorry, the max margin is some type of regularization on the parameters that we have. Even though we work in very high dimensional space, the fact that we are trying to minimize something, in this case, we're trying to minimize the margin or maximize the margin, usually helps in terms of limiting the set of parameters or the values of the parameters that we are selecting. And even though we work in very high dimensional spaces, eventually only a small number of points usually, or you know, again, depending on the size of the dimension, but if we go to a reasonable dimension, only a small number of samples are going to have an impact. And if we don't need to fit all of the samples, right, that's the real problem we had with overfitting. We had to fit all the inputs to get through them in the regression model. But if we don't really care about most of the inputs, we only care about the support vectors, this acts as some sort of regularization and leads to relatively good results. So again, this is in practice, you know, more hand waving, I would say, than proof, but it does work very well. And as I mentioned before, we had neural network, everybody used support vector machines. So those were the classifiers that people have used most of the time. Oh, these were the most successful classifiers. Yeah, there's a lot of software support vector machines. I mean, this is on the slides. The last thing I wanted to ask you guys, or ask the class, is about multi-class support vector machines. So we define support vector machines. Remember that in the logistic regression case, we said, you know, we can just define new parameters for each class. But in support vector machine, it's much more problematic, because we said that even though if we change it to 1 or 2 or 3, it doesn't matter, it will be the same. We cannot just add parameters and say, okay, you have a margin between class 1 and 2, and this is another margin between class 2 and 3. We don't know what the order of the cluster is, right? If we had the linear line between clusters, we needed to order the clusters, but maybe there is no ordering of the clusters. So how do we extend support vector machines to multiple classes? Any ideas? How do we extend this idea to multi-class? Right, in KNN, naive Bayes, it was pretty easy. We just either define new parameters, or in KNN just took the majority. That was easy. What about support vector machines? How can we extend it to multi-classes? Yes. Okay. Good. So the answer that people put in the chat is what people do. It is indeed going to do something like 1 versus all. So we can, in order to find class 1, we train a classifier that classifies class 1 versus all the samples from the other classes. So we learn this is one classifier. And then we learn a classifier called class 2, which classifies class 2 versus all the other classifiers, all the other samples. And then we learn a sample of class 3, and and then we learn a classifier for class 3 that classifies. And now when we have a new sample, we use all these classifiers and we select the class that the classifier says is the class for this sample. Okay? Everybody's okay with this? So we do this rather than doing it in one shot like we did in all the other ones. We do separate classifiers, okay, for each of the classes that we have. In this case, if we have 5 classes, we learn 5 different classifiers. So we don't learn 4 and save the rest. We learn 5 classifiers and select the one that, and once we have a new sample, the classifier. Oh, I was waiting for the question. This is a nice idea, but it doesn't work. Because what if 2 of the classifiers claim that this is the same, is this class, right? So classifier 1 tells us that the new sample is class 1, and classifier 3 tells us that the classifier is class 3. Or what if no classifier wants to use this sample? None of the classifiers tells us that they think it's theirs. What do we do, right? I mean, of course, in all the other classifiers, we had multi-class, we would have to assign to one of the classes. But here we can either assign to 2 or 3 or all the classes or to 0 classes. How do we deal with that? So the answer is, yeah, so the answer, as was mentioned in the chat, which is completely wrong because the support vector machine is not trying to optimize this, but this is what people do in practice, is they look, in addition to the classifier result, they look at the margin, right? So each classifier will tell you, I believe that this sample belongs to my class, and also it can compute the margin, right? How much, so let's say, right, I mean, it's the margin is how, or not the margin, but we have a value, right, which is greater than 0, you belong to my class, less than 0, you don't belong to my class. We can actually, and we choose the classifier that has the highest value. That's what people do in practice. Now, it's important to realize that that's not a theoretically motivated thing because we are not trying to maximize this value for any classifier. We're just trying to maximize the margin, but we're not trying to maximize how far you are for the margin. As long as you are more than 1 for the margin, I don't care where you are. We already said there's no impact. Still, in practice, this seems to work reasonably well. So again, in multi-class classification, we train a lot of different classifiers, and we select the classifier, and then we have a new sample. If one of the classifiers select that sample and all the other classifiers says this is not ours, that's great, then you're done. But if 2 classifiers or none of the classifiers select this, we look at the margin, and if it's a positive margin, we take the highest positive. If it's a negative, we take the lowest negative. That's how we do the classification. Okay, so this is the way people actually use multi-class support vector machine. As I mentioned, I should say there are other ways of doing it. I mean, this is just one heuristic. There are other ways, but they're all heuristics because support vector machines, at least the way it was originally defined, was not defined or was not meant to be applied to a multi-class classification. So we do 1 versus all, and then we compare the margin, and we are done. Okay, so even though it's, oh, sorry, I didn't show. So even though this is not the, the most theoretically justifiable thing to do, in practice, that's what a lot of the classifiers do. And again, support vector machines have been applied quite a lot. At some stage, they were the state of the art, especially for images. Nowadays, we know very well that neural networks are doing better, but if you compare, for example, digit recognition, which is basically a sort of image analysis, again, depending on exactly which, but simple neural networks with only 3 layers or 4 layers, we're getting, so nearest neighbor was doing reasonably well. Simple neural networks, not convolutional, but simple neural networks with a few layers were getting between 1 and 1.5% error, and back then, this was several years ago, support vector machines were doing the best. Nowadays, of course, we can get much, much better with convolutional or deep neural networks, but at least that was the case. Okay, good. So I actually have a demo for support vector machine, but we are running out of time. I will ask the TA to present it and go through some examples, and it shows examples on margins and on changing the value of the error weight in the non-linearly separable case. So you will see this demo, and of course, he will provide the link. You can play with it yourself to see that basically support vector machines or how the impact of adding more samples or changing the weight of the classifier or even changing the kernel, so that demo also has different kernels, is impacting the success of the classifier. Okay, so this will be in the recitation on Friday. And that's it for support vector machine. I think the next lecture is actually going to be on neural networks. Finally, maybe I'm wrong actually. Let's see. Yeah, so next time we are going to neural networks, and after that to ensemble classifiers. Okay. Yeah, so see everybody on Wednesday.